All right, so it's my pleasure to introduce Samuel, who is a postdoctoral researcher at CSH Vienna, focusing on human behavior and network inequalities in social system, and as well as polarization. And yeah, I'm glad that he'll tell us today about multidimensional homophily and intersectional inequalities um, in these networks. Well, with that, Samuel, take it away.
Thank you, Moritz, and thank you all for inviting me. I'm super excited to share my research and to hear your questions. I don't know if you do normally questions during the talk or after, so whatever it is, just interrupt me when it is time. So yeah, again, thank you for having me. And yeah, I would like to talk to you today about this project on how multidimensional social interactions impact intersectional inequalities of social capital. And to talk about that, the first thing that we need to discuss are the basic fundamental social forces that drive our choice of social ties or social connections. And arguably one of the most important one is homophily, because very recent research has shown us that in simple systems with two interacting groups, one minority and one majority, homophily has a well-defined effect, let's say. When homophily is high, then the minority group tends to be disadvantaged. And when it is low, meaning we have heterophily, so preference rather for the out group, then the minority is advantaged. And as you can imagine, however, most of the real life social systems present homophily rather than heterophily. This kind of social visibility inequalities are important, not only on their own, because of course that impacts the visibility of the culture of certain marginalized groups or whether their voice are heard in policymaking, but also because they impact second order inequalities, such as, for example, wealth inequalities. So then it is important to understand how these visibility inequalities emerge, right? The problem is that so far we only know about these simple one-dimensional systems. However, we are not one-dimensional, right? People are defined by a complex combination of characteristics: gender, age, nationality, ethnicity, socioeconomic status. So to model social interactions properly, we need to have a multidimensional perspective. And we should also take into account that to understand inequalities properly, we need an intersectional perspective. What does this mean? This means basically that a person that belongs to several marginalized groups at once might experience inequalities in a fundamentally different way than a person belonging to maybe just one. And we should also ask ourselves what happens with people that are in the intersection of privileged and disadvantaged groups simultaneously. How would they experience these social visibility inequalities? So to answer these questions, in this project, we first developed a network model of multidimensional interactions, and then we applied it to kind of build a framework to understand intersectional inequalities of social capital. So let's begin with the model. The key question that we need to answer when coming up with a multidimensional model of social interactions is how do we integrate information from our multidimensional identities to choose with whom we connect. And this is very nicely illustrated by Paul DiMaggio and Phyllis Garrett in this paper, where they ask, how would, for example, a female Hispanic college graduate who prefers to associate with people like herself in gender, ethnicity, and educational attainment choose her friends? And they consider several possibilities. There might be others, of course. Would she, for example, try to make friends with people similar to herself in all three dimensions, so that her multidimensional group acts as a single category? Would she connect to people based on an average of the three preferences? Would she maybe avoid people from a certain category, like with according to some exclusion principle, like for example, maybe high school dropouts? So to answer these questions, we built a modeling framework. So it's not a single model. We didn't want to kind of choose how one way in which we integrate all this multidimensional information when we interact with each other. Instead, we built a modeling framework that we can use to test different hypotheses about how this actually happens. So let me tell you how this framework works. With a very simple example of a two-dimensional system with two categories per dimension. In one category, we have sex or binary gender, if you want. And in another dimension, we have race, so basically white or black in this case. So the framework works like this. Let's say that someone is evaluating whether or not to connect with someone else. The way it works is that we assume that that person has some one-dimensional connection preferences. Then they would evaluate this preference in one dimension, and these preferences are modeled as partial connection probabilities. These probabilities is basically, this probability describes how much they like the potential target person along one single dimension. So it's like they toss a coin in one dimension to evaluate these preferences. They toss a coin in the other dimension, because here we just have two dimensions. And then the key point is, how do we combine these two probabilities into one final multidimensional probability of whether or not the connection is formed? And it is in this aggregation process where we model our aggregation mechanisms, let's say, where we formalize these possible hypotheses about how we aggregate this multidimensional information. Again, there are many potential ways in which we could do this, and we have considered three. But of course, if you had other hypotheses, you could still test them with this framework. So we have considered again three different aggregation functions, two extreme ones and one intermediate. So one extreme one could be that people are very picky. So they only make connections with others with whom they feel high affinity in all individual dimensions. And we have called this aggregation function AND. Or in the other extreme, it might be that people are really tolerant, so it is enough for them to feel high affinity along one single dimension to make a connection. And we have called this aggregation function OR. And in the middle, it may be that they make an average of all their preferences along each dimension. And by the way, mathematically, this is equivalent of people first choosing a random dimension to interact and then interacting according to their preference along that dimension. And it is very informative to see what kind of social networks these different aggregation functions generate. So let me show you how we can build such a network. We start with a set of nodes completely disconnected, and we start picking pairs of nodes. We look at their one-dimensional preferences, we choose some aggregation function, and then we compute this probability, final probability of connection, and we see whether the connection is made or not. We'll repeat this for many pairs of nodes until we have a network of the size that we predefine, and then we have a network. So let me show you one specific example with these specific preference matrices that, as you can see, they are homophilic preference matrices because they have high values in the diagonal and low values in the anti-diagonal. And for example, if we use the AND aggregation function in this case, we have this kind of network. Here at the bottom, you can see the relative proportion of links between multidimensional groups. Good. If instead we used the OR aggregation function, then we have this other kind of network. As you can see, groups here are much more mixed than in the AND aggregation function that is quite modular. And then the mean aggregation function is kind of in between them. So Cool, now we have a model that allows us to generate different networks depending on the disaggregation functions, preference matrices, etc., etc. So the question is, which of these aggregation function is the one that we use in reality? And I would like you to try to answer this question in your heads, because I will give you the answer in a couple of slides. So to answer this question, we used data, specifically data from 70 high school friendship networks from the US that contain information about the sex, the race, and the grades of these students. And this is one example of one of those networks in one of the schools. So as you can see, students are relatively segregated according to the dimension of grade. Basically, they are segregated by grade. The grade here correspond to different symbols, but they are also quite segregated in the dimension of race, because we see how white and black students kind of are separated into two modules. So what we did was we used Bayesian model selection to test all these competing aggregation mechanisms by fitting them to real data, such as this one from this network and the other 69 schools. And we computed some performance metrics and see which of the aggregation mechanisms performed the best. And these are the results for the network that you can see here. Basically, we used a case information criterion to decide or to measure the performance of the different metrics. This includes both the goodness of fit of the model and also the complexity of the model. So basically to avoid overfitting. And as you can see, the aggregation function is better than the alternatives. And also, we didn't only include or consider these three aggregation functions, but for reference, we also included a fully multidimensional system. This is the first column that you see here, where each category is one full multidimensional group, such as, for example, Asian boys of 8th grade. So yeah, we have our result. The aggregation function seems to overperform the others. And actually, let me tell you that these are the specific results for this school, but this is consistent across every single school that we have looked at. So we have our answer. How would this female Hispanic college graduate choose her friends? Well, she would evaluate her preferences independently in each dimension and then make a connection if her evaluation is kind of positive in all of them. And this model, I think, is very cool and useful because we can use it, for example, if we feed it to data, to recover the latent one-dimensional preferences. So here, for example, we have the preference matrices for the relevant dimensions in this school, which were gender, race, and grade. I'm not going to stop to analyze them. You can ask me later. Just so that you have also a very brief, broader picture of how these preferences look like in these high school networks. These are the distributions of preferences in the dimension of, again, grade, race, and gender. And basically what we see is that all of them are quite homophilic, and we see interesting and meaningful interpretable patterns, such as, for example, in the dimension of grade, we see that, of course, students prefer to befriend others, classmates from their own grade, but besides that, they tend to prefer to connect with students of higher grades than students of lower grades, probably because of this age-related prestige that is going on in high schools, of course. So cool, we have the model, but let us remember that we wanted this multidimensional model to understand intersectional inequalities of social capital. So let's see how can we do this. Let us first remember what happened in one-dimensional systems. In one-dimensional systems, things were very simple. If we had strong heterophily, the minority group was advantaged. If we had strong homophily, the minority group was disadvantaged. In multidimensional groups, we expect things to be significantly more complex. And this actually connects with a very long tradition in the social sciences, which is this research on intersectionality, which basically says that, yes, multidimensional inequalities are much more complex and we should be careful when dealing with them. And something that it highlights throughout many papers and discussions is that these multidimensional inequalities can be fundamentally different from the inequalities found in one-dimensional systems. So this is what we focused on in this project. We focused on identifying these aspects of multidimensional inequalities that were fundamentally different from inequalities found in one-dimensional systems. And let me show you more explicitly or more specifically what we mean by that, using again a two-dimensional example. So we have again a two-dimensional network model with two categories per dimension. Now the categories are going to be the minority and the majority per dimension. We're going to use the aggregation function because we have already validated it with data. And we are going to use these homophily or preference matrices here that are parameterized by one single homophily parameter that we can tune between 0 extreme heterophily and 1 extreme homophily. So we are going to generate many networks with different homophily values, and we are going to measure inequalities of social capital, but by simply looking at the degree distributions of the different social groups, one-dimensional groups and multidimensional groups. And we are going to use a 1 degree inequality metric that I'm not going to stop to explain. You can again ask me later, but it is very simple. This is a metric that we are going to measure for each group. So each group will have one associated value that goes between -1 if the group is fully disadvantaged with respect to all the other groups in the system, and +1 if the group is fully advantaged with respect to all the groups in the system. So what we do is first choose one population distribution, like this one. Basically, you see here in percentages the relative sizes of the different social groups, one-dimensional and multidimensional. And we tune this homophily parameter, changing the preference structure, and we measure this degree inequality metric that tells us whether a group is advantaged or disadvantaged in a given context. Solid lines are here the result of some analytical expressions that we could derive from the model. And very important, if you look at these first two plots, dashed lines here are the results of the inequalities that we would observe in equivalent one-dimensional systems with the same population distribution and with the same preference structure. And we see already something interesting, which is that basically the values, the literal quantitative values that we measure for inequality are very different, right? And we have called this simple intersectionality, the simple direct quantitative differences in the inequalities that we observe in one-dimensional versus multidimensional systems. But we also observe more interesting stuff. And the more interesting stuff we have called emergent intersectionality. And these are the inequality patterns that are not observable in one-dimensional systems. If you remember, in one-dimensional systems, the minority is always advantaged in the heterophilic regime and disadvantaged in the homophilic regime. And here, maybe I didn't say this, but maybe you saw it when I showed the population distributions. These lines are labeled according to the relative group size. So 40% means that here this is the minority in dimension 1, 60% majority, 41% minority in dimension 2, 59% majority of dimension 2. So what we are seeing here is that the minorities in both dimensions are advantaged at both ends of the homophilic spectrum, which is something that is not observable in one-dimensional systems. And finally, we have also, this is the highlight from what I have just said. And finally, we have also identified another aspect of intersectionality. Something very central to the notion of intersectionality is that multidimensional inequalities are very often not discomposable as a simple sum or combination of one-dimensional ones. So here we have operationalized this idea by saying that multidimensional inequalities, for them to be considered truly intersectional, they cannot be linear combinations of one-dimensional inequalities. So we have taken our actual multidimensional inequalities, we have fit them with a linear model, with a linear combination of the corresponding one-dimensional inequalities, and we have checked whether, in general, we could reproduce these multidimensional inequalities just by using this multidimensional linear fit. And this is not the case in every case. And this is one example where they are clearly very, very different. So yes, our model reproduces this notion of intersectionality, and we have called this phenomenon nonlinear intersectionality. And just to finish, these are results of a synthetic network of simulated of a simulated system. But the point, of course, is that this whether this model helps us to understand inequalities in the real world. So if you remember, we already used the model to fit real-world friendship networks. So we can do it again and see whether we can reproduce the inequalities that we observed there. So again, I'm not going to stop to analyze the inequalities here, but these are basically the distributions of the degree inequality that we empirically measure in these 70 high school networks. And here you see in the x-axis versus the y-axis, the empirical versus theoretical inequalities predicted by the model. And as you can see, they align pretty well. So to conclude, we have seen that people aggregate multidimensional connection preferences by evaluating each dimension independently and form ties if all evaluations are positive. We have seen that we can use the model to infer latent one-dimensional preferences and identify different aspects of intersectional inequalities in social networks, simple intersectionality, emerging and nonlinear intersectionality. And also that the model is actually useful to predict these real-life inequalities, meaning that now we can use the model to run what-if scenarios. What if in this school, where maybe there's this group that is segregated, we tweaked the system a bit by maybe changing the composition of the groups, the population distribution, or maybe convincing certain students to maybe be more tolerant to that group or to another, always considering that different attributes might be correlated, so then preferences in one attribute might affect network structure in another, etc., etc. This is things that we can always do with our model. And with this, I'm done. Thank you very much. And I would also like to thank my two wonderful collaborators, Maurits and Fariba. And here you have the two papers that came out of this project. Thank you.
Great. Thank you very much for this exciting talk. And I think we open this up for questions now. So if anyone wants to start.
I'd like to start my question.
Sure.
So thank you very much for your talk. I really like this concept, but I have some kind of like question in mind. Like with this kind of like mechanisms, like this multidimensional like homophily, what you are explaining is mostly like saying that we can represent this society by these kind of factors, but can we really just say like a kind of like number or a vector and say like, okay, the whole network is like driven by this mechanism? Like for example, like with computing homophily, we can say, okay, if the homophily was more than 0.5, like we could say like if it is a homophilic network. if it is near to zero, I can say it's like a not homophilic network. Can we try to like go in that direction and see like we can try to have a vector or like I don't know like one value saying like how this mechanism is presenting the homophilic behavior or like a heterophilic behavior.
I don't know if I understood your question. Is your question whether we can have several values of homophily or heterophily for each dimension independently, or maybe I missed the...
No, like for example, if I have like one dimension, I can
Yeah,
say like for one dimension, I have one homophily value.
yeah,
But here you represent like a matrix format or like multiple matrices.
yeah,
So using these multiple matrices or like a huge matrix, can
yeah.
we also define like a homophily measure that pays attention to all the dimensions rather than only
Um,
one dimension?
whether you can have one single value. I guess that's the question. We never tried, but also because I don't know whether that makes sense. I mean, sociologically speaking, because if I go back to empirical results, for example, here,
Yeah.
if I go back to empirical results, the thing is that connection preferences along each dimension are very different. So do you really want to conflate all of this into just
Mhm.
one value to say that this network as a whole is homophilic or this network as a whole is heterophilic?
Mhm.
Probably you would lose so much information that it might stop being useful. For example, if you aggregate all that information and you have hypothetically a network based where people are connected based on maybe nationality and socioeconomic status. You could expect people connecting across socioeconomic status more or less following some heterophily principle, because, for example, it is beneficial for people from lower socioeconomic statuses to connect with people from higher. So it's like cross-group connections. Then probably based on nationality, because of cultural similarities, etc., you usually tend to have homophilic preferences. If you combine the two, I don't know what you would have into one number, I mean, but if you combine the two, you lose that level of detail, and it might be the point where you actually lose fundamental information that you actually need to understand the network. That's why we never tried. I
Okay.
don't know if there's a good way to do it, but we never tried. Thank you.
Mhm. Thank you.
Maybe I can ask a question. Thank you, Sam. This is a really cool talk. I was wondering if you've tried any kind of like parameterizations for these homophily matrices. Like for instance, with the race, you have like 5 different categories here. It's not just in group and out group, but like there's
Yeah.
some other kinds of mixing patterns between them. Does your framework account for that? Maybe I missed it. First,
Um, in principle, yeah, thank you for the question. So in principle, we treat all these potential preferences as free parameters. Some people kind of pre-structure their matrices, saying we have in-group versus out-group. So, I mean, in this case, for example, with this high school, if you look at grade, you have 6 different groups. So it could be that you just have diagonal versus off-diagonal terms, and that's it. And it's like 2 constants. No, this is not what we do, as you can see here.
yeah, okay.
However, we do normalize things afterwards for 2 reasons. First, for interpretation, but also because otherwise the model is misspecified. We have too many free parameters. So we let this vary, and this is also what let us find patterns like in this case, if you see, well, first of all, this is normalized so that every row is divided by the value in the diagonal, meaning everything is referenced to the in-group preference. So if you see a number that is close to 1 here, it means that that group wants to connect to the other group as much as they want to connect to themselves. And that's why we also don't have values in the diagonal, because they would always be 1 just by construction, not by anything else. And interestingly, you see how still the values close to the diagonal are high. I mean, they are highlighted there. So basically, naturally, students tend to connect, besides with their own people from their own age, with people of similar age, things that make sense. Does that
Yeah.
more or less answer the question?
Yeah, absolutely, definitely. Yeah, I mean, so maybe I'll ask one more follow-up question too.
Please.
There's a lot of like in the community detection literature, there's a lot of thoughts about community detection and metadata. I think this is a really interesting application of what is essentially it's looking at a kind of community structure, but just taking the metadata as fixed. Have you thought about other kinds of like latent like sources of multidimensional homophily or heterophily?
Yeah, honestly, and not yet, but also I'm also aware that people from the community detection line, they have done work in this direction. We haven't, basically because we are interested in looking at preference related to characteristics that we can observe directly. Basically, I mean, metadata that we can observe. In the case of community detection, of course, you are more interested in identifying network structures, usually modular and assortative, but not always, right? So then what happens with these models is that sometimes they are interpretable, and sometimes it's tough to interpret them because they are the result usually of some compression algorithm or something similar. So this is what we wanted to focus on, something that is fully interpretable. Of course, that will mean that we will kind of lose some network information from, I don't know, spontaneous, endogenous, demographically unrelated friends groups, or groups of friends that are related maybe to other tastes, like, I don't know, to people that go and play football together or that share music taste, that kind of thing. If it is not explicitly in the network, you lose it, of course. But what we observe, at least, we can be more or less certain that it is correctly captured. In the sense that because we control for as many dimensions as we can, they hopefully don't, I mean, not hopefully, but we know that the ones we observe, they won't affect each other because it doesn't matter how correlated they are.
Very cool. Yeah, it makes a lot of sense. It's a really cool model and a really cool framework. So yeah, makes perfect sense.
Thank you, Eric.
It's
Nice.
possible. I would like to make a small follow-up.
Yeah.
I just like think about like these kind of models. I feel like maybe like if we have like a minority and majority group, if the minority group like they want to grow and become like majority, maybe they just do the or function, or like they do the and function because they want to like preserve the society that they have, like the within like community preference that they are interested in. So like if the minority people are trying to use different kind of like mechanisms, like how this like network can be generated differently if all the network were using, for example, the OR model or like the AND model. Like have you like worked on this direction as well?
We didn't test what would happen in the case of inequalities when we change the aggregation function. We only looked at the end because it was a validated one, but it would be definitely interesting. But also from my side, it would be interesting if we could find real life, real world systems where we actually observed people using other aggregation functions. However, I'm not sure whether we would observe them because this is so simple that it kind of makes sense. We have results from cognitive science saying that when we are faced with complex tasks, we tend to simplify, let's say, the task as much as possible and use very parsimonious methods to solve the task. In this case, the task is aggregating information, and this is, I think, the simplest way in which you could do it. But yeah, definitely, if you change the way people aggregate information, the outcome will be different. I see it very likely that if people use, for example, other aggregation function than the AND, because it's like the most, let's say, the picky aggregation function, if instead you use the OR, probably you would observe less inequality because groups would mix much more. Might be that in some contexts that's what it is used, but we haven't looked at that.
Okay. Thank you so much.
Thank you.
Well, thanks for all the questions and for the kind answers. So maybe we transition now to the second part.
Yeah. Let me stop
I don't know. Do you have slides for that or?
Not really. I was thinking more about a semi-structured discussion, if it's okay with you.
No, yeah, totally. Just wanted to ask how you would like to start.
Yeah, so basically, the discussion that I wanted to open is how to find your right audience when communicating your research. I don't know about your contexts, and this is more to also learn about other people's experiences because, I don't really have definite good advice on that, but I can tell you about a couple of anecdotes.
Yeah.
So, for example, why I chose this topic is because last year I was participating in a project, in an interdisciplinary project, together with other people that have a physics background, like me, and also a sociologist and a political scientist. And this was a project on polarization. So we aimed at political science, at a political science audience, because we already, or I already had papers on polarization in physics journals. And I think it is important to basically reach the audience that in principle is the most interested one in the topics that you're researching, right? So yeah, having this interdisciplinary team, we decided let's go for this political science journals. We of course started more or less ambitiously, and then we reduced our ambition to lower impact journals. And the thing is that we all grew very frustrated. Also, my political science colleague and the sociologist, because they were feeling that they thought it was a good paper, of course. Otherwise wouldn't make sense. But also they felt that it was much more challenging than they expected to publish the work. And I think it is important to know that they wrote most of the, if not all, the introduction and discussion parts, meaning it was written in the language in principle familiar to others from that field. And in the end, we ended up publishing very, very, very easily in scientific reports, which is, I don't know about you, but for me, it's a very familiar venue for most of the things that I do. If I cannot publish it in super shiny journals, I know the team in scientific reports, if it's something decent, they will accept it. And they were also surprised by that. They were like, but we were so criticized in all these other journals that we know relatively well. We go there. In principle, the language is, it's interdisciplinary science, but I think in scientific reports, at least the things that I have read, they are relatively more quantitative, relatively more like things that I'm familiar with, like social physics stuff. And they were surprised because they were like, we got very good reviews, minor revision, and published. That's it. no suffering, no blood. So yeah, this is how do you reach your audience in this case? I don't know, but as an alternative, something that I like to do is to try to attend conferences, basically of those other fields connected to your interdisciplinary research. And I feel that that is a much more rewarding experience. And hopefully you retain some of the impact that you would have if you were able to publish in these domain-specific journals. Because I mean, people in principle are interested in your research. It doesn't matter that it's published in a more strange journal to them. So that's my starting point. I don't know what if anyone has any similar or related experience that would like to share or advice or anything like that.
I mean, I have a quick question. Do you or does anybody feel like that some disciplines are like less open to interdisciplinarity independent of language? Like even if it were written, as you said, in their language, uh, so, do some disciplines just don't like a lot of insights from outside of their discipline? I have no real experience. That's why I ask. So I would be curious about this if anybody has some insights.
I feel that's the case, but I would also like, I mean, I don't know how interdisciplinary the crew here, like, or if we are all mostly network scientists with similar backgrounds, but I feel like we need to hear from people from those disciplines to actually know what is the feeling there.
Yeah, but then even network scientists are not a very homogeneous crowd, I would say. People are sometimes computational social scientists, a lot of physicists,
Yeah.
some are mathematicians.
Yeah.
Some come, I don't know, from ecology. I know a lot of ecologists who would just end up in network science. So I don't know. It seems like within, I know from some other people that some interdisciplinary areas within network science are easier to convince. So for instance, I have some background in ecology, and in there, people seem more happy with insights from that, let's say, come from a more quantitative side. They're in fact so happy that they sometimes hire specifically people who model food webs or these kind of things. And then I hear from, which is not my experience, so I don't know how true this is, but I hear from some people with an economics background that it's a pain in the ass to try to bring these methods to economics, which I don't know, might be more experiential than just a general thing, but like it's worth to discuss it at least, what the difference is.
Yeah, I think it's totally true that like it depends on the field. I've been, I must say, very lucky because during my PhD, it was like my topic was mainly strictly network science based, and so I didn't have to. I basically talk to myself. But now with the postdoc, I'm entering the more computational social science field. But I think that this one, if you come from computer science, you don't feel like much the limit, let's say, because it's basically uh, I don't know, something that has been going on for quite some time. And I think that from a computer science point of view, it works pretty well. But for instance, I have some friends that works, for instance, with machine learning, and I think that the machine learning community is one of the worst one. I am sorry if any of you belongs to that community, but they are super bad. And also like another friend of mine that submitted like a paper. I don't remember if it was a journal or a conference about linguistic stuff. And he got answered like the language is not good, it's too technical, but it was nothing super technical. It was something like I must say no, normal level, but they got super you know, tricky about the language itself.
Yeah.
And so, yeah, definitely, I mean, it
But this
depends
was
in the field. But I think that also what you said, Samuel, was
Mm.
true. Sorry, I'm talking too much as
No,
always.
go ahead. Sorry to interrupt.
Like what you said was true, that maybe it's easier to start from conferences to get like the flavor of the community, and then adapt and try to find first if it's really the field you want to fit in, and
Yeah.
then maybe I don't know, find the strategy to fit in, something like that, because starting from journals, maybe it's too rough. I don't know.
And people are basically nicer face to face.
Mhm.
They will never tell you to your face that your approach, your epistemology is bullshit, and you should have never come to that field. But
Yeah,
with
yeah,
a bit more diplomacy, you can see that in reviewers' reports.
yeah, yeah. It's like reviewers are the academic version of haters for influencers.
Yeah.
Yeah. I have like another thought that just came up is like sometimes when people say I work interdisciplinary or I want to publish interdisciplinary, sometimes does not really mean being interdisciplinary. It just means you do your own thing, but you just try to solve other people's problems.
Yeah.
And I'm very curious, and I thought more about this because I recently, or like half a year ago, I changed because my professor changed university. I also changed university with him, and the new university is a university that has interdisciplinary in the name, and they try to. So they started new, and what they want to do is um, collect a lot of people that have something to do with computation. So they hired 10 professors and they come from different computation backgrounds. So computation in neuroscience, computation in philosophy, computation in law, like these kind of things. And they try to build degrees, but also an environment where that fosters like real interdisciplinary, meaning that you put a lot of people together and they work together on things and try to learn from each other, and not like to, I don't know, what is the cliche thing of interdisciplinary is like a physicist that takes some model that works in population dynamics and then just does it in, I don't know, some other thing that populates. I forgot. But these kind of things. But like if you develop from scratch some stuff with the language of multiple disciplines, but also like with the types of question you ask, maybe this can be something for the future. Uh, I don't know what point I wanted to make, but this is just a thought that came up.
Yes, something, if I may comment on this, something that we try to do, for example, at the Complexity Science Hub, or that is, I think, part of our philosophy, is that you should, if you're interdisciplinary, you should have all the disciplines at least partially in your own head, not that you are part of a team and, as you say, you do your own thing, and maybe someone else does their thing, and you kind of stitch it together. And I think that's important, that everyone should have enough of everyone of all the disciplines that are part of a project inside their heads. Otherwise, it's impossible to actually develop a proper common language.
Can you maybe share some experiences that you have, or how you make how you not regulate yourself, but as a team, like how to make sure that you're not too one-sided and that you stay humble or be open? Is there anything that you do that works for you? I would be interested in that.
I mean, basically, mutual and infinite patience. I have some collaborations that are very fruitful, but also because I feel we are closer epistemologically, and I mean specifically, I feel very comfortable working, for example, with um, analytical sociologists. That basically is this branch of sociology that is very comfortable doing quantitative research. It's very easy to talk to them because we want to do the same things, just apply them to sociological problems. It's just that we have slightly different ways to think about the methods, etc. It's much more difficult to talk with someone, as Alessia was saying before, that with whom very, very basic technical aspects can be difficult to grasp. And in that case, I feel like there's no other way than having even more of each other's discipline in your heads, because I don't know, I'm always afraid that, for example, a domain expert misinterprets some computation or simulation that I did, and they kind of build a narrative that is basically wrong because they misunderstood. So I try to understand as much as I can of how they interpret things, how they see things, and I try to make them understand as much as I can what are the aspects of this quantitative analysis that maybe I have made that we should focus on to do these interpretations. But I don't have a magical formula. But I do have this experience, for example, with this more interdisciplinary project where they couldn't even understand a heat map. So going very slowly and maybe also even removing aspects of the analysis that are too technical, if you feel that you can kind of communicate them in another simpler, more straightforward more straightforward way, a way that is more understandable. And I don't know, to me, other thing that works a lot, but I don't know if that would work in many cases, is being very graphical, drawing a lot.
I I can say something like we always like normally like hear from the people like saying, okay, we talked to these social scientists, like they did like we presented them, but they didn't understand like what we are doing because we were coming from the computational background and like this kind of stuff. But I have like also an opposite like point of view. Like I was I normally like watch some kind of like YouTube videos like from the social science like network classes, and like they were talking about a lot of mathematical things, a lot of statistic measures that I've never seen in any paper, like in any paper in network science, that they are built for many years, like maybe more than like 20 years, 30 years, like that we are not really familiar with, and they are super complicated to understand. Even understandable for us, like as a network scientist. But they have done it for many years, but we don't know this kind of stuff because we haven't heard of like that much of statistical analysis and statistical testing. So like I would like to say like my opinion and also like how I perceive is like they are very advanced in statistical analysis and statistical measures, and a lot of cool things, especially on like temporal networks and this kind of stuff. But we don't know the language, and at least I feel it's also so difficult for me to understand these very complicated measures that they have.
Yeah, like a couple of months ago, was the first time in my life I heard of exponential random graphs. I was like, what is that? Why did I never heard of it? And this has like a 30-year history
Yeah.
in the social sciences. It's like, oh damn, maybe I should read into that and look if I missed
Yeah.
something.
Yeah,
True,
as a physicist, the first time that you see that, you are like, okay, suddenly there are thermodynamic ensembles that have been studied in networks.
True.
I think that's
And I
also
fully agree. There are parts of this analytical sociology that I think we should try to merge better together with other aspects of network science, and try to also not be redundant, because I think we all know about some stupid redundancies that we as a field have done.
no, I think that's a great and very positive and more actionable point to leave the discussion for today. So, like, thank you very much, everybody, for joining and for the very active discussion. And well, see you next time.
Thank you, Samuel.
Thank you again for having me.
Thanks.